Now we come to the final implementation of DTFT in a loop form. And this time we are going to take both sine and cos into account and recover our full spectrum back. And let's see what happens. So here this is the most elementary implementation of discrete time Fourier transform. Here what we are doing is, again, we are generating a signal. So my original signal, which I'm going to be analyzing using DTFT, is having amplitude of 2.5 units. It is having a frequency of 4 Hertz. And my second signal, I'm going to mix this signal 1 with another signal, which is at amplitude 1.5 and is at 11 Hertz. And I'm also going to introduce a DC component in this signal. And I'm going to take all these 3 signal components, signal 1, signal 2, and DC component, combine them together to make the final composite signal. So this is what is the signal under test. And I want to then use DTFT or the dot products and use a harmonic oscillator which is generating multiple frequencies to figure out these hidden frequencies in this composite signals, whether the detector is able to detect DC, the signal component 2, which is at 11 Hertz, and signal component 1, which is at 4 Hertz. And also the amplitudes must be correctly detected. So how I'm going to do it is exactly the same thing which I've just shown to you in the previous sections. What we are going to do is we are going to generate a certain points, Fourier time and Fourier coefficients, where I'm going to save the Fourier coefficients. And this is the same loop as shown in the previous code block. Now instead of just using the sine to generate the harmonics, I'm using a complex waveform. I'm using the exponential function with imaginary part inside it, minus imaginary part. And this, as we have seen earlier, this the real part of this exponential generates the cos, and the imaginary part of this exponential function generates the sine wave. And then I'm going to use this and calculate the dot product with my original signal. So I have this original signal, and I have this second signal which is generating harmonics, and I'm going to do a dot product in sum and multiply format, and then do some kind of normalization. And just so that I plot these frequencies correctly, I'm going to limit myself to the Nyquist criteria, which is sampling rate by half, and do certain manipulations so that my amplitude is recovered correctly. So let's see whether I'm able to detect the frequencies in this composite signal correctly or not. So here we are. So this is time axis. I have a signal which is going from 0 seconds to 2 seconds. It is containing multiple frequencies. So this blue dotted line, which is having an amplitude of 1, is the DC component. And then there are 2 sinusoids mixed together at 2 different frequencies, and that's the reason why it's a complex sinusoid, not a pure sinusoid. This is my original signal. And then I am going to do a dot product of this particular signal with multiple harmonic frequencies to figure out the original underlying frequencies, which is what this loop is all about. This is exactly what this is doing, trying to find out the dot product. And here is this complex oscillator which is generating multiple frequencies. So when I do that, something very interesting happens. So I have, if you remember, I have 2 sinusoid signals, one at 4 Hertz and the other at 11 Hertz. Let's go back. So I have one signal at 4 Hertz and the other signal at 11 Hertz, and I also have a DC component of 1. And when I take the dot product between the original signal and the complex oscillator, I'm able to recover my DC component. Now this axis is Hertz, x-axis. So I have an amplitude of 1, which is equivalent to DC component of 1. At 4 Hertz, I have an amplitude of 2.5, which is exactly what is the underlying frequency in this signal. And at frequency 11 Hertz, I have been able to recover an amplitude of 1.5. So 2.5, 1.5, and 1, which is exactly what we have here. 2.5 at 4 Hertz, 1.5 at 11 Hertz, and 1 at DC. We can play around with these numbers. Let's say this amplitude is now 5, or my frequency is 7, and here my amplitude is 6, my frequency is, say, 2, and my DC component is 2. Let's see if my elementary DTFT algorithm, which is just these 2 lines of code, multiplying it by a complex oscillator, and then taking the dot product between the complex oscillator and the original signal. There we are. So as you can clearly see, my DC component has gone to 2. At 2 Hertz, I have an amplitude of 6, and at 7 Hertz, I have an amplitude of 5. I've been able to recover the signal perfectly. So let's just go back to the PowerPoint, and I'll explain what happened here. So let's have a review of what we have seen so far in the Python environment. Starting from the Euler's equation, which is the most beautiful equation in maths. It has been shown in Python that when we insert an imaginary number inside an exponential, it starts to generate cos and sine, sinusoid functions. And this whole expression becomes a sinusoidal or a complex oscillator. If we keep changing this angle theta, the speed at which this vector is rotating decides the frequency of cos and sine. The phase of this vector, it decides the phase of sine and cos. And if we just replace this theta with pi, we know that sine pi is 0 and cos pi is -1. So we bring -1 to this side, and this whole equation becomes an Euler's identity, which is regarded as one of the most beautiful equations in math, because it is unifying various different fields in mathematics, from exponentials to sinusoids to imaginary numbers to irrational numbers to rational numbers, everything. And what we've learned in Python is that this complex oscillator is a very important one. We can use this complex oscillator to detect energy in a signal. So let's go back now to the original equations of discrete time Fourier transform, and let's try to understand. In fact, we'll just take this first part, because we know that this exponential is nothing but cos and sine as described in the Euler's equation. We'll just leave this part and we'll try to understand what's happening. So let's have a look. Let's have a look at this. This is an exponential function. It is a complex exponential. It has an imaginary part, and in this imaginary part there's a function, there's a number called k, and that k is nothing but 2 pi multiplied by k into n divided by n. And what it means is that this is a discrete time Fourier transform. So time axis has been converted into discrete steps. So it's and those steps are defined by this number of samples, the S rate, and the harmonic part is defined by this number n. And what it is doing is it is generating multiple frequencies, both in sine and in cos. So here is a cos function, and the real part of this exponential is generating cos signals at various harmonics. And the imaginary part is, you can see it's a sine function, and it's generating multiple harmonics of this sine. So this part is taken care of. Now comes two parts. So one is this xn. Xn is nothing but the original signal, and we are trying to figure out in this original signal what are the frequency components and what are the DC components. And how we are doing it is by using two operations. One is that we are multiplying this signal with this complex exponential, and then we are using this sum part. This is exactly what is dot product, and we are using the dot product between the signal and the complex exponential, and using this whole equation as an energy detector, we are able to then figure out the dot products and their magnitudes. And as we have seen, if the frequency of these signals that are being swept through matches with the frequency of the underlying signals, of the signals under test, then the dot product has a very large detection. It has a very large magnitude, as seen here. So for the DC component, it has been able to, so there's a DC component in this signal, this blue dotted line at magnitude 1. So the DTFT algorithm has been able to detect the DC component at 0 Hertz, the frequency axis is here. And there are two frequency components at 4 Hertz and at 11 Hertz with certain magnitudes, 2.5 and 1.5. And the dot product has been able to recover that magnitude part. So essentially this entire complicated looking expression is just conveying only two things. Take a frequency oscillator, which is generating frequencies in quadrature, and quadrature is another term used to represent orthogonality or 90 degree. So it is generating sine and cos and multiple frequencies of it, and then multiply it with the original signal and then sum it up. Basically, this dot and this summing is nothing but dot product between these two entities. And the resultant output is the dot products. And those dot products have some magnitude. Those magnitudes are going to be large if the frequency that is being generated by this oscillator matches with the frequency of the original signal. That's all there is to this whole equation. And the other way of representing this equation is in the Euler form, where this complex exponential can be split into cos and sine components. So this is exactly what has happened here. So rest up to this part, everything is the same. This exponential has been split into two parts in the sinusoidal form. The real part of it is cos, and the imaginary part of it is sine. So it's as simple as that. There's nothing more to it. If you just understood the concept of circle, and if you just understood the concept of dot product, this is exactly what is happening here. In the next section, we'll try to understand the inverse Fourier transform.